Dr. Roberto, sir, we are going to start the session. Are you online, sir?
Yeah, okay, thank you.
Okay.
Hello
Can
everyone.
you hear
As
me?
we head toward the final session of the National Seminar on Fractional Calculus Dynamic System, we continue our exploration of groundbreaking research in fractional calculus. Good afternoon, everyone. I am Bholanath Kungadkar, MSc final year student from Department of Mathematics, RTMU. It's my honor to anchor this session where we have the opportunity to learn from the distinguished expert in our field. In this session, we have two remarkable talks lined up. The first talk is variable order fractional operator, a new perspective, which will be given by Dr. Roberto Garappa from the University of Bari from Italy. And second talk is fractional derivative with respect to monotonic function tempered approach, which will be given by Dr. K.D. Kucho. To lead this session, we are honored to have with us Dr. Mahesh Wavre as a chairperson. Dr. Mahesh Wavre is a distinguished academician and research renowned for his significant contribution to the field of mathematics. Now, to express heartfelt appreciation, I invite respected Dr. G.D. Kedar sir from the Department of Mathematics to come forward and present floral tribute to our Hello. So I request Mr. Dr. Dhade sir, Kade sir, to give the floral tribute to our estimated chairperson, Mr. Dr. Mahesh Wavre sir.
Okay. Can you hear me? Because I can't hear you very well. You can hear me?
Yes, sir. We can hear you.
Okay. I will share my screen now.
Yes, sir. After introduction, your lecture is going to be start just for 2 minutes.
Oh, okay.
Sir, we warm.
In the meanwhile, I share my screen. Okay.
Now I request Chairperson Dr. Mahesh Wavre to introduce our first distinguished speaker.
Good evening, all. Respected resource person, Dr. Roberto Garappa, today's speaker. Respected convener, Dr. Keda sir, Dr. Gade sir, all participants. I am here to introduce today's speaker in the session 5, online session 2. So we are privileged to have Dr. Roberto Garappa, a leading researcher in the fractional calculus, as our first speaker for this session. Dr. Garappa is full professor of numerical analysis at the University of Bari, Italy. His research focuses on numerical solution of differential equation and approximation of special functions critical areas in the development of fractional calculus. His notable achievements are he authored over 70 papers in high-impact peer-reviewed journals. He developed MATLAB codes for solving fractional differential equation, which is widely used by researchers nowadays. He is specialized in variable order fractional operators, on which he is giving talk today, bringing new advancement in the mathematical modeling. Today, he will be giving a talk on variable order fractional operators, a new perspective. This talk will explore novel approach to depending fractional variable order operators and evolving concept that enhances the flexibility and applicability of fractional calculus in a significant time in problem. So let's welcome Dr. Roberto with big round of applause. I welcome you, sir, for your talk.
Sir, you can start your lecture.
Okay, thank you. I hope you can hear me well because I can't hear you, but I can. I think I can start. Uh, First of all, thank you for inviting me to give this talk. I'm very happy to present this recent research to you. In particular, in just a moment, I will to understand how to. Okay. In this talk, I will first provide the motivations for the introduction of a new variable order fractional operators. The motivation are mainly of mathematical type, and I will show how to derive, and I will show some properties of the new operators. If I will have some time, I will also discuss some problem related to the numerical treatment. I would just like to focus on the fact that this is a quite recent research topic. We started in the 2021, and it is in collaboration with Professor Manardi. I think that Professor Manardi is very known among people working on fractional calculus, and with Andrea Giusti, which is from Polytechnic of Zurich. These are the main papers on this subject that we wrote together. The first one in which it is derived the new approach. The second one concerns the numerical treatment, and the last two are related to some applications, one in probability theory and the other on viscoelasticity. Well, let me see that, as maybe you already know, fractional calculus is used as a tool to model systems with intermediate properties. We know that for elastic materials, we use the Hooke law in order to describe the relationship between the deformation and the force which is applied. And the Hooke laws, the law of Hooke, is actually a differential equation of order zero. We can define in this way. But if we consider a viscous fluid, we have to use the Newton law, which actually is a differential equation of order one. But we know that not all materials are purely elastic or purely viscous. There are a lot of materials which are intermediate, which are viscoelastic materials. This is, for instance, for asphalts, for volcanic lava, but more interesting for polymers, oils, and other materials which show some memory. This is the reason why we introduce fractional order operators. Fractional order operators allows to create an operator which is intermediate between an equation of order zero and a differential equation of order one. What is alpha? Alpha is in some way the rate of memory because this material has some memory, and therefore we have to characterize the memory, in this case by means of the fractional order. However, the memory is not always constant, but also the rate of the memory may change over the time. You can imagine, for instance, the volcanic lava, which is actually like a fluid when it flows out from the volcano. But as it flows, it cools and then becomes more similar to a solid material. The same, for instance, for the asphalt, which is a liquid in the first phase and then becomes more solid. Or, for instance, if we have to describe the dynamics of organic carbon in soils, the properties of the soils, the rate of memory of the soils depend on the season. And so we need a fractional order which changes over time. This is the motivation for introducing a fractional calculus of a variable order. It is important to observe how in the past variable order operators were introduced. In general, this is made starting from constant order operators. Here we have the definition of the classical fractional Riemann-Wheel integral, which is actually this convolution integral with this power kernel, power function kernel. And this is the constant order Caputo derivative. It is important to note that the Caputo fractional derivative actually is the integral of order 1 minus alpha of the derivative of the function. This is very important to note this because the integral satisfies a law of exponents. In particular, we can write the integral of order alpha of the integral of order beta as the integral of order alpha plus beta. And this property, this fundamental property of a Riemann-Wheel integral has an important consequence. Indeed, if we apply the integral to the derivative of Caputo, actually we have a derivative of order alpha of a derivative of order 1 minus alpha. This means that by the law of exponents, we have the integral of the derivative. And then we have in turn the function minus the initial point. This means that we are having last minute because I don't see a part of the screen. Okay, that the derivative is the right inverse of the integral. Okay, and now we see how to obtain fractional order integrals, derivatives of variable order. We start again from the usual definitions of constant order operators, and usually people just makes a replacement of the integer order alpha, the one which is written in the blue color here, with some function alpha of t, which depends on time. This replacement can be made in two approaches, in a direct replacement, as in this case, or in a convolution way by also expressing the order in the convolution formula. Unfortunately, this approach leads to some serious problem. Indeed, the integral operators of variable order does not satisfy the law of exponents. And we remember that this law of exponents, this kind of semigroup property for integral, is the main property which assures that the derivative is the inverse of the integral. So when we perform the generalization to variable order in this way, in general, the derivative is no longer the inverse of the integral. And in addition, we have to say that it's very difficult to find the inverse of an integral of this kind. It is useful to focus on the fact that this property, or better, these issues, were known since 1993. There is a very important paper by Basanko and Ross, which indeed discusses this point. But the absence of the law exponents and the fact that the derivative does not invert the integral when we generalize constant order operators to variable order operators in the classical approach leads to some serious problems. Indeed, usually when we want to solve a fractional differential equation, also, for instance, with this variable order operator, in general, we convert the differential equation in integral formulation, and we apply some quadrature rule to this integral formulation. For instance, the product integration rules on which it is based the predictor corrector method devised by Witten and others is based on this approach. We commute from the differential equation to an equivalent integral equation. But unfortunately, with variable order, the two problems are no longer equivalent. They are different problems. So if one follows this approach, actually is formulated one problem, but is solving a different problem. And this clearly leads to an error. Unfortunately, there are several papers in which the differential equation is formulated in the integral equation, and then people actually solves a different problem with respect to the problem that aims to solve. Thus, to overcome this problem, we have studied a different approach. This different approach consists basically in not generalizing from constant order to variable order in the time domain, but to perform this generalization in the Laplace transform domain, and then now I will explain how it happens. It is useful to say that this is a new idea. Indeed, it was sketched by an Italian engineer about 50 years, more than 50 years ago, in 1972. But these ideas were disregarded for long times, maybe for the absence of a general theory supporting these operators, also for the absence of robust numerical methods for the inversion of the Laplace transform, because as we will see, we need methods for inverting the Laplace transform in order to handle these operators. But also I think that these ideas were disregarded because they were published actually in Italian languages, and unusual Italian language is not very known among the mathematical community. Okay, and now let's start to see how to define the new variable order operators according to this new approach. Actually, we start again from the classical definition of the Caputo derivative, which is actually the convolution of the derivative of the function with this kernel phi, which actually is this weakly singular function, the function of phi. We just confine for simplicity to the case in which alpha is between 0 and 1, but some generalization can be also possible. We see that the Laplace transform of this kernel actually is this power, the power alpha minus 1 of S. So if we consider the constant function, we consider alpha of t as the constant function, its Laplace transform is this function capital A of S, which is actually alpha over S. And then we can write the Laplace transform of the kernel, which is actually S to alpha minus 1, in terms of this function capital A. So when we see the function alpha t as a constant function, as it happens in the constant fractional calculus, we see that we can write the Laplace transform of the kernel as this function in terms of A. But since we have S to power S time function A, capital A minus 1, we can do the same also with the Laplace transform of any function alpha t. So if we consider a variable order function, the function which describes the way by which the order changes over the time, and we can compute the Laplace transform of this function, we can produce a new kernel in which we use now the Laplace transform of this kernel. And then we can invert this Laplace transform and obtain a representation of this kernel in the time domain, and then define the variable order derivative in terms of an integral, of a convolution integral, exactly as the previous definition of a constant order of Caputo equation, but now the kernel is obtained as the inverse Laplace transform of this kernel. Clearly, the same can be done also for the integral. Indeed, also the integral can be seen as a convolution integral in which the convolution kernel is this function psi of t, and we can compute the Laplace transform of this kernel, which is actually s power to minus alpha. And we see that in the constant case, when alpha is a constant function, the kernel, the Laplace transform of the kernel can be expressed in terms of this function capital A. And usually we can do the same also when we have a variable order function alpha of t, which varies, for instance, in the interval between 0 and 1, and we obtain a Laplace transform of a kernel psi of alpha in this way. Also in this case, we can invert this Laplace transform, obtain a representation of this kernel in the time domain, and define an integral of fractional order or variable order in this way, exactly as we made in the previous case for the constant order. So we now have a derivative of variable order obtained with this kernel, which is the inverse Laplace transform of this function. We have an integral. We have to ensure that they satisfy a kind of fundamental theorem of fractional calculus. We need to ensure that the integral, the derivative, is the right inverse of the integral, so that we obtain this condition that it is in blue in the middle of this slide. And we know that thanks to the Stoney condition, this is ensured when the two kernels satisfy this integral equation for any value of t. However, it's very difficult to satisfy this condition, or better, if we have the kernel of the derivative, it's very difficult to compute the kernel of the integral, which satisfies this equation in the time domain. But this task is very simplified if we act in the Laplace transform domain, since the two kernels must satisfy an algebraic equation of this type. This is the counterpart of the convolution equation that we have on the left. And we can see that we will consider the two kernels, the kernel of the derivative and the kernel of the integral of the variable order, we see that they actually satisfy the sum condition, Stoney condition. So we are sure that with this approach, that one operator is the inverse of the other. In the other case, when we do the classical approach, in general, we do not have integral derivative, which are one the inverse of the other. We see some properties that must be satisfied by these kernels. Indeed, both capital phi and capital psi must be some Laplace transformers on function. So necessary condition is that their limits for s tends to infinity is 0, and we can compute that this means that the limit of s times capital A of s is some values strictly included in the interval between 0 and 1. And this means, thanks to the theorem for the initial value of the Laplace transform, that the limit of the function defining the variable order alpha of t for the limit for t tends to 0 must be any value strictly included between 0 and 1. This means that actually the kernels must be non-regular. They have to they must be weakly kernel weakly singular kernel. And in general, this is a very known properties that the fractional order operators must be must have a weakly singular kernels. So the problem is that now we have good operators from the theoretical point of view, but actually we do not have analytical representation of the kernels. We do not have analytical representation of the derivative or the integral, but we know the behavior just in the Laplace transform domain. And so we do not have an analytical solution of the Volterra, of the variable of the fractional differential equation. This is the reason why it is essential to have good methods for the numerical inversion of the Laplace transform. Indeed, if we want to compute this kernel, we need to invert the Laplace transform. We have studied the method based on modified Talbot methods, in which actually we use the formula for the inverse Laplace transform, which is actually given on a Abramovich line in the region of convergence of the Laplace transform. This this contour is deformed. This Abramovich line is deformed in a suitable contour. In this way, the integral can be represented by me as a line integral, and this integral can be truncated, and some quadrature can be applied to evaluate the integral by means with a given tolerance which is chosen. In particular, but maybe these are just details which I will mainly skip. We have chosen a parabolic contour, which is very simple but also very powerful, and we have used a truncated trapezoidal rule, and by performing an error analysis involving discretization error, truncation error, and random error, we are able to find the parameter defining the parameter, the parabola, mu, the step size for the quadrature rule and the number of nodes in order to obtain a tolerance and accuracy epsilon. This method is studied in the paper by Wedman and Trepeten. It's a very nice paper which I recommend. I would like to show something with some function describing this alpha t describes an exponential transition between a first value alpha 1 and the second value alpha 2. So we are modeling the derivatives which starts at, in this case, from 0, say, from 0.6 and arrives to 0.8. The Laplace transform of this function is given here. And as you can see, the kernel of the derivative is given here with the black line. And you can see that in the first phase, it behaves as the kernel of the derivative of order alpha 1, but on long times, it behaves as the kernel of the derivative of order alpha 2. This means that we are actually having a transition from alpha 1 to alpha 2. The same happens with... I can hear, but I understand I will conclude right now, okay? This is the kernel of the integral, and we have the same. And we show similar result with a different function in which we have an order starting from 0.6, arriving to 0.8, and then decaying exponentially to again to 0.6. And we see that for small time, for early time, long time, both kernels behave as the kernel of order 0.6 of the constant order. Okay, I think I have to skip or more detail devoted to the numerical computation. I think that there is no enough time. I expect this, but you can read this result on our papers. And here are some examples of simulation of Brusselter systems of variable order. And also in this case, we realize a transition from the first order to the second order. And we just briefly discuss some problems. The first problem is to obtain a transition not only from order between the 0 and 1 from general order. We have not studied so far this problem. It is useful to study methods with a higher order of convergence because our methods so far is just first order, and also to handle with transition function which the Laplace transform is not known in an analytical way, and to study other applications. Okay, here is some references. The first two, the original paper by Scarpi, then our papers in which we illustrate the approach of variable order, some papers devoted to some applications, hence some paper which we used for the numerical treatment of differential equation of variable order according to this approach. Finally, two very interesting papers, one by Coach Bay, the other by Lucico. I think that any people working fractional calculus should read these two papers because they actually gives properties for derive new operators of fractional orders. These are very, very useful, very interesting property. Okay, I think that my time is concluded. I would like to thank you everybody for listening to my talk, and also to the organizers for inviting me. Thank you.
Any questions? Any questions from audience? Dr. Robert, sir, there is a question from audience.
I wish you had slightly more time. Did you work on periodic fractional order? Periodic fractional order.
Sir, did you work on periodic fraction order? Did you work on periodic fraction order?
No, I not working on a periodic fractional order, but that would be interesting to work on. So far, we have worked on some transitions from one order to the other, but not on periodic. But I think that it's an interesting topic, especially for describing seasonal effects, since during years you have some periodicity of this kind.
Any questions? Okay, let me conclude this lecture here. Thanks, Dr. Roberto Garappa, for your really new talk on variable order fraction operators. Initially, you mentioned why we study fractional calculus by mentioning the relationship between deformation and applied forces. With nice example of changing the material state of, he explained why we study fractional calculus of variable order. He also explained the alternative approach to variable order fractional derivative and integral also. Like fundamental theorem of calculus, he stated the fundamental theorem of variable order fractional calculus with numerical experiments. He told what are the future scope in this regard, the variable order fractional operator. It was nice, wonderful, and informative talk for us. Thank you, Doctor. Thank you, Dr. Roberto.
Okay, thank you to you. Thank you very much.
Thank you, Dr. Roberto Garappa, for your insightful presentation. Now I request our chairperson, Dr. Mahesh Wavre, to introduce our next distinguished speaker.
Dr. Roberto, sir, you can go offline also. Means if you want to leave the session, you can, sir.
Okay. Okay, thank you.
Once again, good evening all. This is today's last session by Professor Dr. K.D. Kuche. We are honored to have Dr. Kuche here, a history mathematician and academician. Dr. Kuche sir is associate professor at Department of Mathematics, Shivaji University, Kolhapur, Maharashtra. Within over 20 years of teaching experience, he has significantly contributed mathematics education and research. His research area includes fractional differential equations, abstract differential equations, integral inequalities, dynamic equations on time scales. His notable achievements are more than 50 research papers he has published in Scopus, Web of Science, and yes, Sky Journal. His citation is 400 plus, H index is 22, I10 index is 35 on Google Scholar. Recently, he guided 4 PhD students, and now at present 3 students are working with him. His major research project funded by SERB and UGC with the grant exceeding 40 lakhs. Invited speaker at International National Conference, USA, Brazil, Spain, China, Saudi Arabia. At present, he is the chairman of Board of Studies of Mathematics at Shivaji University, Kolhapur. Dr. Kuche has played a key role in organizing several national and international conferences on differential equations and fractional calculus. Today's his talk will be on fractional derivatives with respect to monotonic function, a tempered approach. This talk will provide insight into how fractional derivative can be adapted to monotonic functions using tempered approach, enhancing their flexibility in mathematical modeling and applied sciences. So let's welcome Dr. K.D. Kuche with big round of applause.
Thank you very much, sir, for a nice introduction. Can you hear me, sir?
You have 20 minutes here.
Yeah.
Okay,
So,
sir.
can you hear me, sir? Can you hear me?
Yes, sir.
Can I start, sir?
Yes, you have 20 minutes, sir.
20 minutes. Oh, no issue, sir. I will stop sharply at 5:25. Okay. Thank you very much, sir, for giving me an opportunity to talk at National Seminar on Fractional Calculus and Dynamical System. Today, I will talk on fractional derivative with respect to monotonic function on tempered approach. This is my outline of the talk. Firstly, we will discuss brief review about the fractional derivative, and we will discuss why it is necessary to have the generalized fractional derivative. Then we will discuss why necessity of studying tempered fractional derivative. And one derivative we have constructed, that is tempered psi fractional Hilbert derivative. We will discuss its properties, and if time allows, we will discuss the fractional differential equation associated with it. This presentation is based on this research paper, which is published in Chaos, Solitons, and Fractals, which is co-authored with Aaron Fernandez, Fahad, and my research student Mari. We know the fractional calculus is generalization of differentiation and integration, the operators of classical calculus to non-integer order. Okay. We know the studies in field of fractional calculus is motivated either by mathematical curiosity, because fractional generalization often produce new properties and challenges that does not exist in classical case, or by real world applications, as fractional derivatives are useful for modeling different type of phenomena, for example, viscoelastic process, non-local interaction, and many other processes. We know the start of fractional derivative. It was a discussion between Newton and Leibniz, okay, in 1695, and from that a number of derivatives appeared in the literature, and we can find there is no unique way of defining fractional derivative. Okay, so therefore, if you see the literature, there are there are number of definitions of derivatives. Okay, if we search the literature, there are more than 25 definition of fractional derivatives are appeared in the literature. Okay, so why this much of derivative definitions are there? Okay, so new fractional derivative is generally proposed with the two aim. First aim is that to capture mathematical properties which the existing fractional derivative does not have, or to model some physical process for which existing fractional derivative is inadequate. In that sense, we are defining the new fractional derivative. Okay. Now, whenever the new fractional derivative is defined, what we are expecting that fractional derivative must satisfy these properties, 1 to 7 properties. Okay. It must give a backward compatibility if you are giving the zeroth order to it, means function as it is. Then if you are considering means real order is replaced by, means order is replaced by natural order, it must give your classical derivative. Linearity property should be there, commutative property should be there, index law must satisfy by that fractional derivative. That derivative, fractional derivative must able to give the Leibniz formula, and chain rule shall be available for that fractional derivative. But unfortunately, if we see any derivative, even though most well-known derivative, that is Riemann-Liouville and Caputo derivative, that these all seven properties does not satisfy by any fractional derivative in general. Okay. But Riemann-Liouville and Caputo satisfy most of these properties. That's why these derivatives are the well-known derivatives in the field of fractional calculus. Okay, so we know a whole theory of fractional differential calculus, maximum theory of fractional differential calculus is developed in the theory, in the language of Riemann-Liouville derivative. Okay, because it plays important role mainly in the development of theory of fractional derivative. But when we consider the differential equation associated with Riemann-Liouville fractional derivative, the initial condition appear that gives fractional order initial condition, which has no clear geometrical interpretation as well as physical interpretation. Okay, but Caputo has that property. Okay, the Caputo fractional derivative gives rise the classical initial conditions rather than the fractional derivative, which make Caputo derivative more suitable for considering the fractional differential equation associated with Caputo derivative. Now, already I have discussed that there are a lot of derivatives available in the literature. Okay, so if we observe fractional derivatives definition of fractional derivatives are given in the form of fractional integration. So many definitions are given in terms of fractional integration. And if we observe fractional integral equations, their kernel we can combine at one place. Okay, so that we can have a generalized definition of fractional integration. And we can try to combine all these fractional derivative under one roof. Okay, so that we can have a generalized fractional derivative with us. And studying differential equation with different type of derivative, okay, is not necessary. Okay, if we have the generalized fractional derivative with us, we can study differential equation associated with generalized fractional derivative, and all differential equation with other derivatives came as a particular cases. Okay, so it is necessity to have one generalized fractional derivative operator which combines these all the derivatives at one place. Okay, so that we can study the theory of fractional differential equation under one roof. The first attempt in this way is proposed by Hilfer, who has introduced two parameter derivative, alpha order derivative of beta type. Here beta allows between 0 to 1. If you are taking beta equal to 0, it gives you Riemann-Liouville fractional derivative, and if I am taking beta is equal to 1, it gives Caputo derivative. Then there is a concept of fractional derivative and fractional integral with respect to another function, and that concept first introduced in the book of Osler, and it is studied in the research monograph by Kilbas in the fourth in the article 2.5, and Samko et al. In this research monograph in the article 18.2. Okay, so this is the definition given by Osler. The initial definition. Okay, it is the concept like Riemann-Stieltjes integration. We have the Riemann integration. Okay, integration of function f of t with respect to t, variable t. Okay, so can we have the concept of the integration with respect to another function? In that sense, this is the concept of the Riemann integration, Riemann-Liouville integration with respect to another function. So if you are considering psi is monotonically increasing function, which is positive, having continuous derivative, then the integration of function f with respect to the function psi in the sense of Riemann-Liouville is defined in this way. Alpha order integration, okay, it is given by 1 upon gamma alpha, and psi integration from a to t psi dash of s psi t minus psi s. We can observe that if I am taking identity operator here, it is reduced to what your usual Riemann-Liouville definition. With having the definition of Riemann-Liouville fractional integral with us, the concept of Riemann-Liouville derivative, in sense of Riemann-Liouville derivative, is given in Kilbas, the research monograph by Kilbas, which is this n time operator 1 upon psi dash t t d by dt operated on n minus alpha psi Riemann level integral. Having motivated by this definition, Almeida in 2017 given the definition of psi Caputo derivative, which is given in the sense of Caputo. It's n minus alpha psi Riemann level integral of n time operator operated on f of t 1 upon psi dash d by dt. So already we have discussed the concept of Hilbert derivative, which combine the concept of Riemann level derivative and Caputo derivative. Okay, having definition with us of psi Riemann level Caputo derivative, psi Riemann level derivative, and psi Caputo derivative, we can combine this definition. Okay, thinking in that way, Souza and Oliveira in 2018 introduced this definition of Hilbert derivative with respect to another function. Okay. And it is proved in that research paper that this definition gives number of derivative as the special cases. Special cases. Okay, so this definition has two parameter. One is alpha is order, beta is the type, and psi is the function. We are taking the derivative with respect to another function, which is given in this format: beta into n minus alpha order psi Riemann level integral of this n time operator operated on this integration of order 1 minus beta into n minus alpha psi Riemann level in the sense of psi Riemann level. Okay. And this is another concept of tempered fractional derivative. Okay. So we can see fractional derivatives and integrals are convolutions with power law. And if we multiply by exponential factor, it leads to a concept of fractional derivatives and fractional integrals. So a lot of literature is available related to your tempered fractional derivatives and tempered fractional integral. The tempered fractional derivative is the modification of actually a standard derivative that incorporate an exponential tempering. Okay, if we know if the usual system is not working, what we are doing, we are disturbing the system. Okay, so in that sense, we can disturb the derivative concept. Okay, by tempering by some factors. So here exponential function is used as the tempering factor. Okay, and this tempering helps to control the singularity. Okay, we know Riemann level derivative and Caputo derivative are defined in terms of integration, and that integration have the singularity. Okay, so the tempering concept control the singularity and long-term effect typically seen in the fractional calculus, making it useful in application where memory effects decay over the time. So the most important application of temporal fractional derivative is that it operates, if we consider it, it can exhibit semi-long range dependence and find application in various fields like stochastic process, finance, and geophysics. These are some examples I have mentioned here. It's control the singularity. The temporal factor prevent the singularity behavior in the standard fractional derivative. Unlike a standard fractional derivative, which exhibit infinite memory effect, the tempered version allows us for the exponential decay of the memory interest, and it has application in physics and finance. So most important application related to the tempered fractional calculus is given in the research papers by Sabjikar that we have mentioned in the references 14, 15, and 16. Okay. So what we have done, we have combined the concept of tempered calculus, derivative or integration of the function with respect to another function. Okay. These combiningly give new operators. That combiningly gives us a new operator. Okay, so to define the concept of psi tempered derivative, we require to define firstly a concept of tempered fractional integral of order alpha. Okay, so here it is considered that alpha and lambda are the complex number having real part positive, and psi is increasing function. Okay, whose derivative is positive. Then the tempered fractional integral of order alpha and index lambda with respect to function psi for the integrable function is defined in this way. Okay, so you can see here is the tempering term is observed. Okay, e raised to minus lambda psi t minus psi s. Okay, which allows to remove the singularity of the fractional integral. Okay, so if you are taking lambda is equal to 0, it converted to your psi Riemann level integral, and if we are taking psi t is equal to t and lambda is equal to 0, it convert to your usual Riemann level integration. Okay, now question is remain when existence of this integral. Okay, and it is proved that this integration is exist for a real part of alpha is positive. Okay, And it is only to avoid this non-singularity at s is equal to t, and there is no assumption is taken on the parameter lambda, which we can take any complex number, okay, because this function is bounded as well as continuous on the finite interval, okay. So having concept of Riemann-Leibniz integral in the tempered sense, we are free to define the concept of tempered derivative, psi tempered derivative in sense of Riemann-Leibniz as well as in the sense of Caputo. Okay, so that definition is appeared. This is the definition of ordinary tempered derivative. Ordinary tempered derivative. So first order psi tempered derivative is given in this sense: 1 upon psi dash t d by dt is equal to lambda. If I am taking lambda is equal to 0 and psi t is identity operator, this tempered derivative is converted to your classical derivative again, and its nth order derivative is defined in this sense. So it is n time operator operated. Okay, this is operator 1 upon psi dash t d by dt plus lambda. It is n time operator. It is given a symbol like this. Okay, and having this concept of nth order derivative, psi tempered derivative in classical sense, we can have the definition of tempered psi Riemann-Leibniz derivative. Okay, so you can see in the definition of Riemann-Leibniz, one component of integration derivative of function with respect to another function, that is with respect to psi, is considered. Parameter lambda is there. Tempering parameter, we are calling it lambda. So it is defined in the sense of Riemann-Leibniz, just like how we are defining the Riemann-Leibniz derivative is nth, if n is sandwiched between order alpha is sandwiched between n minus 1 to n, then how you are defining Riemann-Leibniz derivative, it is classical nth order derivative of n minus alpha order Riemann-Leibniz integration. In the same way, just a classical derivative is replaced by n times psi, is nth order tempered psi derivative, and your usual Riemann-Leibniz integration is replaced by tempered psi Riemann-Leibniz integral of order n minus alpha. So this gives the definition of tempered Riemann-Leibniz fractional derivative. On the similar line, we can have the definition of tempered Caputo fractional derivative. Okay, just this order is interchanged. Okay, but having this concept with us, we have attempted to extend this definition in the sense of Hilbert. Okay, so this is most generalized definition we have introduced. Okay, and the work related to it's published in the elsewhere journal Chaos and Soliton. Okay, so this concept of Hilbert derivative we have extended to tempered psi Hilbert derivative. Okay, so we are having here three additional parameters, say beta, lambda, and function psi. Okay, so having chosen different values for beta, lambda, and psi t, we are getting different type of derivatives. Okay, and see here in the definition of Hilbert derivative, just we are replaced here tempered psi Riemann-Leibniz integral in place of usual Riemann-Leibniz integral. Okay, classical integral, classical nth order derivative is replaced by this operator. And again, psi Riemann, this usual integration, Riemann-Leibniz integration is replaced by tempered psi Riemann-Leibniz integral of order 1 minus beta into n minus alpha. And we have proved that this definition can be written in this format. Psi Hilbert derivative format we can do. So you can see here multiplying factor is appeared, which is tempering term we are considering here. Okay. Now, see here, as your Hilbert derivative interpolate between your Riemann-Leibniz derivative and Caputo derivative, similarly, this tempered psi Hilbert fractional derivative interpolate between what your tempered psi Riemann-Leibniz derivative and tempered Caputo derivative for the values of beta equal to 0 and beta is equal to 1. And this gives the general idea about how the derivative we have constructed is the most generalized version. If we consider lambda equal to 0, tempered fractional order derivative converted to your classical operator. If we consider lambda equal to 0 in psi tempered derivative, it converts to the psi fractional derivative. If you consider psi t is equal to t, psi operators become a classical operator, okay? And if you consider psi t is equal to t, then psi tempered fractional derivative become a tempered fractional derivative. And if you are considering lambda equal to 0, psi t is equal to t, psi tempered fractional derivative become your classical fractional operator, okay? Here, the definition which we constructed is the combination of Hilbert version, which is generalization of Riemann-Leibniz and Caputo derivative, fractional calculus with respect to another function, and a tempered approach is added. Okay. In this sense, it has many special cases which have previously been studied in other work, and some of the special cases is specified in this table. Okay. So if we consider psi t as it is, beta is equal to 0, this tempered psi Hilbert derivative is converted to tempered psi Riemann level fraction derivative with respect to function psi. Similarly, if you are taking beta is equal to lambda as it is converted to tempered kappa. So here we have specified some of the cases only. Okay. Whole number of derivatives we have listed in the research paper. So one can see that. Okay. Now, to study differential equation associated with it, okay, since this is generalized version of derivative and it incorporate different fractional derivatives, okay, if you consider the differential equation associated with different fractional derivative, we require a different solution space. Okay, so in that sense, we require a generalized solution space. So this generalized solution space is introduced in the research paper of Souza and Oliveira. Okay, so this is weighted space is a space of weighted continuous function of order 1 minus gamma. So here we are considering the function f, which may not be continuous, but after having this weight multiplied with it, it is a continuous function, and its norm is defined in this way, and this is your Banach space. And when we deal with the solution related to it, associated with it, okay, so we can find the solution of differential equation associated with this in solution space. Okay, so I'm not going into detail again. So it is proved that this tempered Riemann level integral of this power function is given in this format. So which we have obtained in the form of this well-known Cummins function, or we are calling it confluent hypergeometric function. Okay, if you are giving the value psi t is equal to 10, lambda is equal to 0, this integration of power function is converted to our usual power function, Riemann level integration of power function. Okay, and here also we have obtained derivative of power function for tempered Riemann level fractional derivative with respect to the function psi. Okay, so see here we have discussed only the power function, because other function we can write in the terms of power function, like exponential function is the convergent power series expansion, has a convergent power series expansion. Okay, sine cos has a convergent power series expansion. So having the integration and derivative of power function with us, we can find out the derivative and integration of your trigonometric function as well as exponential function. Okay. This is if alpha is between n minus 1 to n, and if alpha tending to n, this tempered Hilbert derivative with respect to the function psi is converted to what your classical nth order tempered derivative with respect to psi. Okay. This is the right consistency we have obtained, but it unable to give the left consistency.
You shall, sir, conclude within 2 minutes.
Yes, sir. Yes, yes. Thank you, sir. Thank you. Okay. So these are some properties, sequential properties, which we have proved here. Okay. This tempered Riemann level operator is bounded linear operator. And this is the differential equation associated with the tempered psi Hilbert derivative. Okay. And it generalizes many differential equations whose existence uniqueness we have proved through the fixed point theory. Okay, this is the equivalent integral equation which we have obtained for the differential equation, and through it we have obtained the existence and uniqueness result, as well as this continuous dependence result we have obtained. Due to lack of time, I am unable to explain this. Ulam stability, different kind of stability we have considered here. Okay. So the conclusion is we have introduced most generalized version of the derivative, which incorporate many derivatives as the special case. Okay. So if you are studying differential equation associated with the generalized derivative, other differential equations with different kind of derivatives appear as a particular cases. So in that sense, this theory is important. Okay, thank you. If someone have a point to discuss, we can discuss. Thank you, sir. Thank you very much.
Questions from audience? Questions from audience? Thank you very much, sir. In this talk, he explained various temporal fractional derivatives like phi-Hagler, Riemann-Liouville, temporal capital fractional. Some results on this. He also told about visual scopes. He started with fractional derivative with respect to monotonic function. Initially, he gave brief review about fractional derivatives and he told about whatever definition of fractional derivatives you are using, it should satisfy certain properties like identity, linearity, commutative, chain rule, etc. Whatever definition you are using. He explained there are 11 cases of definition of temporal fractional derivatives. Thank you very much, sir.
Thank you very much, sir. I thank organizing committee for giving me an opportunity to talk in this conference. Thank you very much, sir. Thank you very much. May I stop sir, here?
So just vote of thanks is there, and after that you
Yeah.
can.
Yeah, first.
Thank you, Dr. K.D. Kuche, for this compiling and thought-provoking presentation. Your session provides us deeper insight into fractional derivatives in relation to monotonic function using the tempered approach. Okay, now I kindly request Dr. Gade to present a certificate to Dr. Mahesh Wavre as a token of appreciation. Dr. Gade. Concluding this session, I would like to invite Mr. Rishikesh to deliver the vote of thanks.
Thank you, Bulana. Good evening of everyone. I, Rishikesh Kapgate, student of MFE first year. It's my great pleasure to give vote of thanks on this special event. First, I want to extend my heartfelt appreciation to our respected chairman, Dr. Mahesh Wavre, for his support and guidance. His vision and leadership have played a crucial role in the success of this event. I would like to extend my heartfelt thanks to Dr. Robert Gasper for his engaging presentation on variation order factor operators, a new perspective. Your discussion has opened new perspective and inspired us to explore more further this area of research. Additionally, we are profoundly grateful to Dr. K.D. Kuchefer for his enlightening presentation on fractional derivative with respect to monotonic function tempered approach. Your extensive knowledge and deep explanation have significantly enhanced our comprehension of this subject. Lastly, I would like to thank all the organization community, participants, and all research scholars. Thank you.
Thank you, sir. It was great pleasure to hear from you. You can, sir, stop the meeting.
Thank you. Thank you very much. Thank you very much.
Students, the session is over for all of you. So you can leave and you need to come tomorrow by 9 a.m. sharp because breakfast is between 9 to 10 a.m. only. Got it? And council members should be present before 9 a.m. Okay?
सर मीटिंग राहू द्या. हो नाही एंड करा मीटिंग राहू द्या. किती लोक ऍड होतील हे सर मला वाटतं ठीक आहे सर नाही नाही नाही
Okay, otherwise I can do
हो सर ठीक सध्या राहू द्या रेकॉर्डिंग स्टॉप करा.
I want to carry at least to the guest house for my daughter. I'll be happy to see. I'll keep inside the guest house. But that also can